All right, let's get started. All right, so announcements. Homework 4 was released. It'll be due a week from today. We'll have office hours at 3 to 4 again. And again, if you guys need extra office hours, please reach out. We have grade exams, probably 92% last time I checked, graded. So we should have those, I'm hoping, by Tuesday night, if not Wednesday. All right. Any logistics questions? And for you guys that just came in, we'll talk about the exam on Wednesday, and we'll give you grade distribution so you can see how you fare compared to everybody else. The class is graded, do not worry. Yeah, or curved, sorry. The class is graded and curved. Both are true. Yes?
So you curved like the whole class, or you curved each exam?
That would be effectively the same.
Okay.
So it's usually the whole class. It just makes it easier. Yeah.
Are you curving including the labs and stuff too?
The entire class is curved. That is either good or bad. I don't know. It depends how you like statistics, I guess. Any other questions? Those are fine questions. Okay. So last week we talked about interrupts, and you guys were very good about interrupts, and we got through almost half of the NVIC stuff. But today we'll talk about, finish up the NVICs, maybe get to interrupts and preemption in more detail. There's a couple extra assignments or walkthroughs that we can do as well. And then, let's see, after that, I mean, really, the first half of this course is all about the core and memory map I/O and getting things to the peripherals. And so we assume you know that by now, right? You know, the mystery of loads and stores into registers. Those registers have these other functionalities that the core doesn't know about. The registers will configure GPIO or whatever. So up to that point, you figured it out. Interrupts are a little bit different. Interrupts are how we're going to deal with the outside world. But everything after that, these are all basically peripherals. That's all these things are. They're just peripherals that do different things: timers, serial buses, ADCs, learning about peripherals, assuming that you know how to or the mechanism for configuring them and using them. All right, so last class, well, let's see. Yeah, so we're going to talk about interrupt control registers, interrupt flow control, interrupt priorities, and concurrent and overlapping interrupts today. We'll review from last time, just because it was a long time ago. Interrupts are basically, the key idea is that it's different than polling. So polling is the idea that you're going to go and check in code every time if the bit is set high or low. Interrupts there, you have a piece of hardware, external hardware to the core. You configure to make that decision for you. That sends a signal to the core to interrupt its process and launch some other piece of code that does something. The two significantly different types of interrupts, although I guess they functionally do the same thing. You have system exceptions or internal interrupts. Those are things that are internal to the operation of the chip. So it could be like some sort of weird execution fault or a bus fault, something that's not necessarily your responsibility as a programmer, something that keeps the chip functioning. Then you have external interrupts or external interrupts, or just interrupts. But the idea here is those can be interrupts that are still generated on chip. You could have a timer that doesn't have anything from the external world, but it's not, it's external to the core. Okay? Now we talked about vector tables. Vector table is where we store the list of our interrupts so that it's the address of the interrupt handler. And so it tells, the NVIC knows where to go, which memory address it should run next and push to the PC. And then to prepare for running the interrupt vector or interrupt handler, we have to stack and unstack. So let's do a little bit more review. If you look at some of your manuals, you'll see this basic configuration. You have your NVIC, which is connected to your peripherals. You have these wires that come through. These are interrupt requests. So these things will go high or low if there's interrupt. And the job of this thing is to figure out what should happen. What should the core do if a particular interrupt occurs? I went through this diagram. Let's see. So basically, you're going along code execution. Some interrupt occurs. You got to go to your vector table to figure out, okay, this wire went high. So one of these wires went high. Which one of these things should be raised? Or should we go to? And there's a few extra special ones we need to look at. This is at the lowest point in memory. So it's the start of memory. You'll have your top of your stack. You'll have your reset handler. This is the bit of code that gets run first. Before anything else gets run, there's configuration things that the core needs to have done to get it to boot properly and run. There are things in here you could edit if you really wanted to, but generally there's no good reason to. In this particular example, this interrupt line is going high, so that gets raised. It's just a single bit, gets raised high. The NVIC figures out, okay, I need to go to memory location 25 or 64 and use that, whatever PC or whatever address is in there is the thing that's going to get executed. All right. And then you go into your interrupt service routine, execute your interrupt, and then you get placed back into code. The core has almost no idea that anything happened. There's probably a ways and reasons why you'd want the core to be aware of it in some ways. You could have some registers or something, or some memory locations that the core could scan just to see what the status is. But generally, the core doesn't need to know. All right, and then last time we blasted through a bunch of slides about great stuff, super great stuff. We talked about there exists a bunch of registers that are going to hold the state, and that's about all we were really covering there. There's different ways to access these registers, but you can disable registers. There's registers for things that are pending. There's registers that control or keep track of what things are active. And we're going to talk about today how you set the priority of these different registers. So, any questions about that very quick review from a week ago? Yeah?
So the NVIC isn't in the core?
NVIC is not in the core. NVIC is part of the core, yes.
Okay, it's like on that diagram, it's like kind of in the core.
NVIC, well, I don't know how we're going to define what the core is, but we can say it's in the core, it's fine.
Okay.
It's part of like the RTL, which is I don't even know what RTL stands for, real-time design language or something. It's part of the code, the artifact that you get from ARM. So it's got the NVIC and the core processor and all the bus structures. That's part of it.
Okay.
Any other questions? All right. Actually, I guess I can say it's definitely part of the core because you can't have a functioning processor without it. There's types of interrupts that must be processed for ARM, even if the manufacturer didn't implement anything. So yes, we'll call it part of the core. All right, talked about that stuff. There are registers. These registers exist. They have this annoying aspect of it that if you want to set and clear them, you actually have two different addresses, one for set and one for clear, even though it's the same data underneath, because the designers want to make sure that you don't accidentally reset registers or do something horrible. All right, but that's not the fun part. Let's go here. Okay, this is where we left off last time. We're going to talk about the sequence of events that occur for interrupts to happen. So in this diagram, we have 3 traces here. This is the processor mode, whether you're in your normal program execution or you're in your handler. You have an interrupt request, which is one of those lines that go high or low from the NVIC, and then you have your pending register status, or pending interrupt pending status. So basically a register just holds which interrupts are pending. So in this particular case, you have your hardware goes high, it pulls this. Within some period of time, usually like a clock cycle, the NVIC will say, aha, this is now pending. This thing will go into the pending register. Now you could have lots of pending interrupts. We'll talk about how we set the priorities of those things, but it's not just that you immediately just get one and then you execute it. You could have lots up there, and so you have to have some register to keep track. Okay, and then sometime later, you're going to go into handler mode. What's happening here? Anybody remember? Yeah.
You're looking up the ISR in the vector table.
Yep. That's exactly right. What else is happening?
You're stacking the registers that you need to.
Yep. So you're saving the state. So first you got to figure out where the interrupt handler is. So where's the code that's going to be run? So that's the first part of the answer. Second part was, well, you got to go save the state of your controller so that when you come back to your core, it's in the right state. So that's go stacking. That's why there is some time delay here. Oh, I forgot to hand these out. Oh, and so we'll talk about there's different ways that interrupt requests gets cleared. So sometimes you can say some with hardware. Sometimes you have to explicitly write to an address in your peripheral that says clear the interrupt. Yes?
Would you have to change the speed of the processor mode, or
We'll have to change the speed of the processor mode. What does that mean?
like you know how like those like fast like rising edges?
Oh, you mean those lines, if this like it was a GPIO line? They're going as fast as they possibly can already. Running the speed of your GPIO line is really, the GPIOs are not involved in here. You don't have access to it, but that's really about what sort of load you expect to have externally on your device. So if you have a load that doesn't have much capacitance or has certain things going really fast, might have it ring, and that would cause signal integrity issues. So that's really why the speed is there. It's basically how much drive strength you get. Yeah, you look. What's that? One more? Okay. Oh, sure.
Thanks.
Okay, so in this particular, the interrupt gets cleared by software or by not software. What did I say? What was the next slide? There are weird cases, edge cases that should probably be thought about. One of them is you could have an interrupt request that comes. Where did I leave off? You guys got some? Thank you. And so the interrupt request, now the NVIC puts it into pending status, and you could have it cleared by software. That seems like a really weird edge condition. How could software even react fast enough for that? The typical case here, we just bring it up to show, is that you could have an interrupt disabled, but you've still configured it to fire off its IRQs. So this happens oftentimes, especially if you're changing your priority. So one thing that's useful is if you're going to rechange your priority levels or enable an interrupt, you might want to clear it off first so you don't have a bunch of old pending interrupts going off. So it could be the case where you actually don't execute it if you clear it in software or some other mechanism. But just an edge case to explain. All right, so here's kind of the normal condition. I'll get you one. The normal condition here would be you have an interrupt request goes off, the processor sends it into pending, then your interrupt, all right, so then you go into pending, then your thread mode changes from normal mode up into the handler through stacking, unstacking. Once you enter, I like coming back here. You guys better watch out. I might lecture from back here now. Once you've gone through stacking, and now you're in your thread handler, then the interrupt goes from inactive to active. That's just a way for the processor to keep track of what things are actually on at that moment. Questions so far?
What is a strip mode?
What's that?
What is a
Slope, because we're doing things here. It takes time. So this is indicating you have to do stacking. So that takes multiple stores. You got to take those, your first 4 registers plus 12, your PC, your link register, your stack pointer, probably something else, and stick it on your stack. So that takes some time. Usually takes about 12 cycles of latency from the time an interrupt service request goes off to the time you're in your handler. All right. What other questions do you have? Yes?
Do we have to manually, like I know we have to clear the interrupt pending. Do we have to manually disable the interrupt request, or is that built into the software?
It depends on the peripheral. You guys don't actually typically have to handle pending. That's just a weird slide. This past slide, the confusing one, this is just an edge condition that says that you can change the pending bit, but you don't have to. Software will de-append it. Once it goes active, once you're here, or hardware will do this, or the NVIC will do it. So you went to interrupt, you went to pending, and then by the action of going from thread to handler and stacking, then it's deasserted. Once you become active, it's deasserted. Yes? Real loud though, I'm old.
Why do you need the interrupt active status if the processor goes into handler mode?
You can have, well, we'll find out later, you can have more than one active interrupt at a time. Yeah.
So is there a different interactive signal for each interrupt?
There's a register that tells you which interrupts are active. Yep, and so this is just more of a diagram just saying this is, we're in that state.
For the interrupt request, what decides whether or not the interrupt request gets cleared by the sub?
Depends how that interrupt has to be done. Usually it's some register you have to go in there and reset the register. So you may be in your handler, you have to go through and say, aha, this is part of your job is to reset that interrupt request.
So like during the middle of our handler mode, it clears it.
Could be, yes. You can also, it depends, you can also have hardware that's clearing itself. It basically gives a pulse instead of holds it high. So that's peripheral dependent, I guess. Yeah, oh, just itching, no worries. Okay, so we'll go to this, this case, and there's no right or wrong answers we're just gonna explore. You guys can fill these out. What happens if the IRQ is not cleared? So what happens if an interrupt service request just stays high the whole time and you get in your handler mode and then you're about to end your handler? What's gonna happen the rest of this? You guys can work together.
I just feel like the pending status is gonna
Interrupt. It will no longer be pending. Yeah.
Is it ever end?
Go ahead. Let me remind myself of the answer. Oh, okay, I know. I remember the answer now.
This diagram looks like I'm looking at the slides. Give it a little bit of time. It looks like it enters handler mode. Then at some point, the handler mode.
When it exits handler mode, then pending is going to be reasserted, or the active can be reasserted. It's no longer active.
Yeah. So what happens if it doesn't know it has to exit?
I don't know. Think about it. Come up with something. Thinking out.
Yes.
Weird.
Well, that's Are you saying that like it'll exit handler mode and then
All right, so what do you guys think? What are some of the possibilities? Got an interrupt request that stays high. Yeah.
The interrupt active status of the processor mode, the processor mode goes back to the thread mode whenever it's done.
Yep.
And the interrupt active status also goes down. The pending status also stays low. The problem happens when there's another interrupt status.
Okay, so it's going to ignore this until there's a rising edge. Pretty close. Okay. What happens if it's not rising? It's not edge triggered. What happens if it is level triggered? Okay. Let's look at what that process looks like. Okay, so I mean, you guys weren't supposed to know this. You're like, the goal was just to think about this, make a guess, and then learn from what happens, right? So I want you guys to think about it. We're not grading these like, I'm not giving it to the graders to be like, oh my God, did they get it right? That's not going to be fun. We're just like, did you participate? That's what we're trying to do. All right. So anyways, request went off, or request got captured, something went into pending. Pending is deasserted because you're in the interrupt, okay? When the interrupt is disabled, now pending can go back up. So pending all of a sudden says, oh, wait, where are my interrupts? Then it reasserts pending. And then this thing basically goes right back into that interrupt. Yeah?
Interrupt re-enter doesn't go all the way back down to thread mode?
This you mean?
Yeah.
We're going to talk about that later. There's a trick here. So one of the tricks would be you could go all the way back down and unstack, and then you have to restack. So we call it tail chaining. It'll be at the end of this lecture. Basically, there's a shortcut if you know there's another interrupt right there. Yep.
Is there unstacking and stacking occurring when the interrupt is re-entered or just restack?
Here?
Yeah.
So the naive way to do it would be unstack, see that there's another interrupt, and restack, knowing that that is something that the processor can anticipate in the sense that if you know you're going to have to go back into it, just don't unstack, basically. That's the trick. But we'll get to that. Okay. What happens if you have multiple interrupt pulses, but you're about here. You haven't necessarily responded to that first pulse. Like by here, you haven't responded. What do you think is going to happen to the multiple pulses? Are we going to do the interrupt multiple times? Or are we going, like, what are all the possibilities? Why don't you go work together, think about some ideas.
The second
Triggering, but I can't do anything about it.
triggering after the first one finished, right? So if the pulse happens during the first one, the second one is never
That's what the interrupt request, the pending status gets cleared, but the asphalt. It'd be nice if you remembered your
Yeah.
So I think if we're like in
So let's make the assumption that these things happen before we can really finish off the interrupt handler, okay? These events are occurring quickly.
unless there's like some something pending going on. Oh wait, my pending's gonna grab another guy. Unless there's a way of like saying, okay, I need to activate it.
So it's a still.
Stay high.
I have another request. That's all it says.
So this one's like because when we enter handler mode, we're using sample like the and now yeah, that seems that allows the actors on you. We're gonna enter handler mode.
Yeah.
So this one's like
And now you're taking back.
I could just hold my pending high until I see them.
Talk about that. That was the whole.
No, that's requested. Like I can hold my pending high while I'm like the pending stats just stay high. Okay.
I'm not sure about that part. What is this?
Okay. What do you think happens if you get lots of edges or lots of interrupt pulses? What's going to happen?
Does pending status just stay high after the first one until processor mode, until it goes active and then it just goes low again?
Why would that be a good idea or a bad idea?
It would be, well, okay, assuming this is for one specific interrupt.
Okay.
If I'm already, like, if I ask for interrupt and I ask for it again, I already asked for interrupt earlier.
Yep.
There's no reason to like go down and go high. And going down and going high can cause issues with metastability maybe, but maybe not. I don't know.
Certainly, you could have a condition where you've got lots of interrupts going off and you can't respond to them, right? And so we're talking about what happens in that case. And so you don't necessarily want to be in the, well, what would be the bad thing with trying to keep track of how many times the interrupt went off? What would you do in that case? Yeah.
You'd need like a register to count it.
You would? And then even, how would you respond to it? Like you'd have to have, I guess you'd have to keep track of how many times it went through, and then have special code that says it went off 3 times before I could handle it. It just gets complicated.
Could you save the interrupt request in memory?
Save the interrupt request. I mean, what does that mean? Like,
Since you know that 3 of them went off, but you can only handle 1 right now, save the other 2.
So I think you could do that. You could say, or you could force the processor to do that interrupt multiple times. As soon as you get in that interrupt, then go back into it and back into it 3 times, right? But I think what would happen is you could have some misbehaving, some external thing that's going off. You might just fill your queue up for a very significant amount of time if you did that modality. So yeah, again, you guys didn't know that, but you're bringing up great ideas about what are some of the edge conditions. So in this particular case, what ARM does, because it's all design choice, is they say, all right, this thing's going off and off and off. I'm only going to respond to it 1 time, right? When I get to it, then I'll respond. The fact that it went off 3 times, I'm just missing information, or I missed that event. I was not able to get to it fast enough. Okay? Yep.
What if these are 3 different interrupts?
Oh, we'll get to that. Now we're only looking at 1 at a time, but we are going to talk about from different peripherals could provide different interrupts. Then you'd have a different line, interrupt request line for each one of those peripherals. If we go back to the NVIC with all the arrows coming out of it, those would each be different, and we'll talk about how to deal with those cases in a little bit. Yeah.
If the pending was shorter, so that it like was low before the last rising edge triggered, would
Yes.
pending status save it?
So let's say if you were, I think what you're trying to say is if we did all our job and got done with active mode here, and so, oh wait, no.
Not even like done. Like, we started active earlier, so that pending had gone
Oh,
down.
shoot, don't say it.
Or like if we spread the 3 bumps further apart.
Yes. Well, it's not going to change the state of anything unless the bump happens over here, like way over here in time, because even if the interrupts or edges are coming while you're active, you still can't set pending. It can't be pending if you're inactive. I believe that's true. Can't be pending if you're inactive. Yes. I believe that's true. We're going to find out. All right. Wait, any other questions? So the big takeaway from this condition is it's the architectural choice is not to count how many interrupts have occurred before you get to it. It just adds a lot of complexity. I'm sure some processor on the planet probably tries to do that. These are also fairly quick events. Here, the timescales have been kind of mushed around for the sake of the example. But this is only 6, it takes 12 cycles to get in here. This is like 8 cycles or something just to stack. So it's not like it's a condition that's common where you're going to even miss edges. At least not in this world. Okay. I think it's our last example here. What happens if you are in, so let's see, interrupt has come, you've gone to pending, your NVIC has caused your processor to go into handler mode, and you've stacked, you're active, but while you are active, you get another interrupt. I guess I was wrong.
Oh wait, it can be. Oh wait, what? Oh,
But you can't come out of interrupt, or you can't. Let's go ahead. Just.
Wait, so we do get to come back? We do get to pend again?
But active's not going to change though, because the pending just went beforehand, right? That pulse occurs while you're still in.
Wait,
So your pending can't go high.
but active stays high?
Active goes low on its own time, and then it can release pending to go high.
Okay, so pending can't go high while active is high.
Correct.
Very cool.
So we're definitely still active here. Here we're going down. The
Yeah.
pulse has already happened, but there's like time delay so that pending can go back up now.
If you look at, I think if you draw those lines just right, there's still time for that thing to go high.
Okay.
What do you think?
So I feel like I heard you say something.
Yeah, I said it wrong probably.
Okay. I thought I heard you say something like you can't set pending when active is enabled.
I thought for sure you couldn't. But now the ARM manual is telling me other things.
I might have misheard what you said. It might be the other way around.
Oh, I think it's from, wait, let me go back. I think it's the difference between edge trigger or not. All right, anyways, I probably made a mistake. Let's figure out what my mistake was. Oh, wait. Well, before I ask you more questions, we all get more confused. Let's just look at what ARM says the answer is. All right. So I believe this is because, so we've gone from interrupt request caused pending. Pending got deasserted when you went into active mode handler. You've got another positive edge triggered here on that pulse, which caused pending to go again. Then active goes low, and then you come back out of that. You're doing tail chaining here. You come back out, and then you go right back into interrupt. So I misspoke before when I said it's, that you can't be, that the only thing that can make pending go high, or sorry, misspoke when you said pending can't go high if you're active. I was wrong. Pending gets deasserted when you go inactive, but then something else can cause pending to go high again. Yeah.
So in that case, can you like re-emphasize like what triggered the pending status again?
Two things triggered the pending status. The pending setting being deasserted is caused by the interrupt going active. You're no longer pending if you're active. So that's why it's deasserted. To be asserted, another interrupt request came. I need to find a state diagram for this, yeah.
What will happen if the first interrupt will take like more time?
This one took long time?
Yeah.
It would be fine. It would still be, this thing would not, so it's getting deasserted, pending's getting deasserted when you went back into the interrupt, right? So this one would just move way over. Pending would still be high until pending gets deasserted by going into the interrupt.
So in the previous one,
Yeah, what did I do wrong over there?
it's like similar. We couldn't like have three.
But 3 pulses happened before you were in it, right? So this one is, these 3 pulses occurred before you got into your interrupt active state. So we've lost that edge information. But I suppose if that pulse happened here, then the pending would get asserted because the interrupt went high. Then pending would get, and then when you came out of this, you would go, okay, I have to go back into it. All right, so now that I messed that all up and you're all very confused, what more questions do you have? Yeah.
So I'm not sure if I missed it, but is interrupt pending status edge triggered or level triggered by the interrupt request? I'm just not sure. Because the first one we did, slide 31, seemed to imply it was level triggered, but I can't quite tell.
I don't think it's ever officially specified. To be honest, we don't get all that insight into the NVIC. We can just say that I think you could claim it's either one.
Very cool.
Yep. This is at some point the hardware engineers say you don't get to know that. It's not that important. All right. I must have more questions because I messed that part up. We can do that lecture again. I'll have to give that one again. What other questions you guys have? All right, well, let's just go through this one more time just to make sure. To raise the pending status register, what's the thing that can cause that to happen? The interrupt request. So that raises it. The only thing that can lower the pending status register bit is going into active state. So one thing raises it, one thing lowers it. And so we can see that here where you went in, it got lowered, but then another interrupt occurred, which raised it again. Okay. Yep.
And I guess like the width of the pending status is the transition from thread mode to Amber mode.
Basically, yep. In this particular case, yeah. Yep. I mean, it can be long if you have lots of things that have been pending for a while. All right, so we'll talk a little bit about interrupt priorities. So we can have interrupts that are more important than other interrupts. What would be an example of when you'd want one interrupt to be more important than another one?
Yeah. Like a boss call me or a friend call me. You gotta like probably pick up.
Oh my God, all right. There you go. So there is idea that some things could be more important.
When you're like trying to turn off something and you want it to like turn off instead of doing whatever other interrupt.
Yeah, that's kind of about the same. There's maybe another idea that there's maybe like ARM has decided that some things are so important for the chip just to function, it must be handled, while other priorities like GPIO lines going higher inherently have less priority. But all those answers are absolutely correct.
I just had another thought. Maybe like one interrupt that just not stop working. Maybe like had some infinite loop or something, so you have another interrupt that can interrupt the interrupt.
Ooh, an interrupt that can interrupt the interrupt. Well, we are going to get there. Not for the infinite loop problem, although that's interesting.
Is it like emergency situations?
Yeah. So, okay. So almost everything on the NVIC is you can change its priorities. And we're going to talk about some nomenclature that's going to hurt our brain a little bit. We have things that are higher important interrupts can preempt lower important ones, which means preemption in this idea that you're doing a priority or maybe you're in an interrupt and you can have something stop that interrupt from going if it's at higher importance. We have a nomenclature problem here, which is that I'm going to try to use priority number or priority value. So lower priority number means higher importance. So now we're going to be in golf rules here. We're always going to, hey, I didn't make this up, okay? I didn't make this slide. This is how the ARM manual uses their terminology, okay? So lower priority number means higher importance. What might be one reason that they've gone with this golf rules sort of, and golf is like you have to get the minimum number of strokes. Why would they do this?
Because 0 is like the first one you actually see on the factor table.
Yeah, okay, there's something there, yeah.
Maybe so that you have like a set value for the highest priority, whereas you can like, if you did it the other way around, you would just get larger and larger.
Right, so that's part of the reason too. So starting with 0 as the most important thing defines everything below it to be, or any higher number to be less important. Because remember, the number of interrupts that can occur is defined not by ARM, they only provide 16, but also by the manufacturer, and you can have up to 240. So in your particular dev kit has 96, I believe. So the problem is you never know what the absolute number of interrupts on your chip is, so you just go reverse order, 0 being the most important.
The negative interrupt you talked about, those count in the 96 that we get, or?
Yeah, plus or minus 16. I don't remember exactly. I think it did actually. I think it was 80 and plus 16. I forget. I don't know. There's a lot of dev kits in my brain. Okay. There are 3 fixed priorities. These are different than particular interrupts. There's 3 fixed priority numbers or values that are reserved for system exceptions, and only one of them can you even kind of mess with a little bit. We'll talk about that. And then these interrupt priority levels or numbers are held in registers, okay? We'll talk about this in more detail, but basically they're values that you can set. You can rewrite and say, I want this interrupt to be more important than that interrupt. This is just a reminder that we're doing golf scoring here. So for instance here we have, you can look through it, kind of make yourself a logical truth table. If priority number of interrupt A is 5 and the priority number of interrupt B is 2, B has a higher importance than A. Okay, B will, if you're running these things, B will always run before A does if the interrupts occurred at the same time or close to the same time. There are a couple fixed priorities, like reset, which is like hardware reset everything. That has the highest priority. That if you get a fault that causes resets, it has to happen. There's other non-maskable interrupts. Second priority, the hard fault is something that you shouldn't, but you can if you had to. You're able to control that one or at least block it off. All the other interrupts are adjustable. So how do you do that? You have ARM gives you 8 bits to set the priority. In your particular dev kit, you actually don't even implement the bottom 4. Okay. You only got the top 4, and then you can, well, as we'll see, we can slice them into 2 different categories. You have the preemption priority and the sub-priority. Preemption priority means of these interrupts that are coming in, this is the one that's more important and can interrupt the next one. Then you have sub-priority means if 2 interrupts are of the same priority, then which one has greater priority. And this helps with this housekeeping a little bit. Yes?
So it's like the sub-priority number like a tiebreaker.
Yeah, you could say that. Yep, exactly what it is. And the tricky part is you get to define which bits are going to be preemption priority or sub-priority. You can make them all preemption priority. I don't think you can make them all sub-priority, actually. But you could make 3 of them or 2 of them preemption priority. Yeah.
How do the 2 instructions still have the same priority? Like
Same.
And sub-priority?
Then the first one that gets in there is the one that gets to go. Yeah.
Can you explain the difference between the 2 sections again? Is it like the blue section allows things to actually interrupt other interrupts?
Correct.
Okay.
And the next one is if you have 2 interrupts of the same preemption priority, this is the sub-priority. This is the one that gets to go first. Or gets to go next, sorry, I should say.
Wait, so something with the same preemption priority and a better sub-priority than the previous, it'll still stop the other interrupt from running, or will it queue?
It will queue.
Okay.
Yep. And so it says, okay, here of all the, I'm in an interrupt. Say my priority is, 5, and I have a whole bunch of other 5s. This is the next 5 that should go. Should be serviced next. Yeah. Then I believe it's whatever's next in the queue. I don't know exactly how they make that last little tiebreaker. Yeah, it's probably, yeah. Maybe the NVIC decides as it goes up the table which one's the lowest value. That's an interesting question. Okay. Why in the world would ARM come in here and give you give you bits that are non-implemented? Why did STM? So ARM gave you 8, STM only gave you 4. Why? Yeah. True, but if why didn't STM use all 8 bits? Why did they only use 4? These are not implemented on your particular dev kit, which, yeah, it's just on your particular dev kit.
Is STM using those 4 bits for their own interrupts?
Nope, there's unused.
There's only 256, so we'll probably not need that much bits. That's the reason.
Yeah, you don't need that bits, and it's just going to add extra complexity, more hardware to interpret those bits. So to lower the complexity of the entire system, because you only have 96 to begin with, you don't need to have all 8 bits. I think there's only 240 that can be made anyways. Yeah. So yeah, you get to set these number of bits. I was wrong. I'm often wrong here, as we found out today, second time wrong. But you can have a preemption priority. You can have 0 bits for your preemption priority, and you can have all these be sub-priority. That would be amazing. And I'm not sure why you'd want to do that, but you have the flexibility to do that. It basically means that whatever comes in first, the interrupt will happen, and you're going to wait until that interrupt's done to go after the next interrupt. And that way, it's like you can't have any preemption, which just seems like a weird idea to me. But some people are smarter than me thought that was important. Okay. I thought this is important. maybe conceptually to give as a warning of why interrupts are so important. And if you're ever going to modify it, you have to know this little piece of information, and you just won't be able to get it to work for like 4 hours straight until you ask Matt. So there is literally a key built into a register that says if you want to change the preemption priority, you have to go and take this key, write the key into a particular register first, and then the next instruction will allow you to change the preemption priority or the sub-priorities. Why is STM, giving you all these extra, like making you have a key to unlock this thing? Probably not security. Nobody's stealing, and let's assume that your little ARM processor is only your software running on it. Nobody's really trying to attack it. Yeah, they're so afraid you'll mess it up, or at least we could say their customers have messed it up so many times, and planes have crashed, or maybe not planes, but bad things have happened, right? Bad things happen but you can just have weird code that rewrites a memory address, and now the thing is hosed. In fact, it may not easily come back up, especially if you have other interrupts, like a sequencing of events to boot. So they try to give you this extra piece of redundancy, just like they did with registers, that you had one for clearing, enabling, when you're enabling interrupts, one for clearing and one for setting. So they're trying to give you extra redundancy to make sure you don't make minor mistakes. Yeah.
So you would just, I guess, how do we use the key then? Can you use this to one of the registers for the interrupts?
Let's see, there's a register that's the key. If I read through the data sheet, there's a register, and you have to take this value and just put it in there. You have to read through the data sheet and say, okay, that's my key, and put it in that thing, and that unlocks it. So then you can go reset the preemption and the sub-priority priorities. You don't believe me, or I'm confusing.
I guess maybe I have to actually do it to see how it gets.
I mean, there's some register. You set a value to it, and that will allow you in your next instruction to reset that register, or the preemption priority mapping. Okay. All right, so you can imagine that since there's 8, they've allocated 8 bits even though you're only using 4. So now you have a memory address, basically, and then you have some memory address, and then each one of your interrupts you can define to have some preemption and sub-priorities. So you're basically going to write bits in these fields, and you can think about just having some memory address, and then you're incrementing by 1 for each byte of data. And you can reform factor that into, when you look through your cube IDE code, right, you're going to have some register value, and you can put all 32 bits in there if you want, or you can write byte-wise or half-word-wise or whatever you want. There is no probably data actually being able to be stored in those lower 4 bits. It's just not going to be implemented at all. All right. So masking is a valuable tool. So say you've gone up and you've set, 10 interrupts to go off, plus you got the system interrupts, and you have some really critical, time-critical piece of code you have to get through. It could be in another interrupt, it could be in main, but every time, if you're running this code, you don't want to be interrupted, so you can set your base priority. You can basically say, there's another register value, any interrupts that have an exemption priority that is lower than this are allowed to go. But anything that's higher than this, we will disable effectively. There will be disabled not by going to the registers and disabling them, but just by saying to the NVIC, do not pay attention to any interrupt with a base priority larger than this value. Yes?
So they don't get anything, they just get straight to the board?
They'll go into pending. They still go into pending. Well, see, I got to stop saying things about how I feel the processor works. I will take a note on that one. Do they actually go into pending if the base priority is lower? That is a great question. I have enough processors between MSP 430 STMs and ESBs that I don't remember all the details sometimes. Does it go to pending? Okay. Any other questions? Yeah.
What happens if you want to ignore a specific interrupt?
A specific interrupt is probably best to just disable it. But this is a way to say, just go by groups.
Well, so if you want to say like, I want the base priority is 4, except there's this one that has a base priority of less than 4, but I still want to be notified of that interrupt.
Well, then you've set your interrupt priorities incorrectly for how you want to architect your system. That's a painful answer. Yes?
Why wouldn't you just give this interrupt a higher priority?
Oh, but it may be, that's true. It may be just that you never want to respond to it. So you're landing your moon lander. You don't care if some other sensor goes off. This is so critical that if a sensor goes off that does something else, just do not pay attention to it. Yes. Correct. Right, and so you would, in a sense, by dynamically programming the value of this register in your main function to say, I want to do this or not do this. Or you could, in your interrupt, some other interrupt, you could say, okay, this one's so critical, I want to set everything else high for some reason, so I don't get interrupted out of this.
So this can be called something that's just a function, not interrupt, right?
Correct, absolutely. This is just a register. You just put data right in that register whenever you want.
And can an interrupt hold this information too? Like we're in the middle of an interrupt and we're like a critical piece of that interrupt.
Yeah.
We can just add those 2 lines of code and then no other interrupt with lower priority.
Correct. That might be an indication that you set up your interrupt priorities incorrectly, right? Because then what you're basically saying is every time I write this code, I want it to be more important than something else, but then you could have gone and just set your interrupt priority and your sub-priorities correctly. So I guess there's 2 ways to survive, to take care of that issue. Probably better to set your interrupt priorities correctly. But that is also going to be very difficult to keep track of what's going on. So maybe not in this class, but they'll have long engineering meetings about what's their priority and who should be able to get this, and trying to keep it all in your head so you have a good idea of what your processor's doing. Okay. There is, let's see. You can disable some of the non-maskable interrupts. Hard faults. And then you can actually, with the fault mask, you can disable, a little bit redundant slide, but the fault mask, you can actually disable the negative level 1 priorities. This was the fault priorities. So this is, your code is so important, you don't even want a certain number of faults to be triggered, leaving only reset handler, and what was the other one? I forget the other handler. The number 3, the highest, and the second highest to be done, the -1 and -2. It's just so you have options. Okay. So let's talk about we talked a little bit about this when you have multiple interrupts going on. Okay? So in these diagrams, we're going to have your program stack. You're going to have your interrupt priority table. So for these 5 interrupts, this is telling you the priority level of those interrupts using golf rules, where the lower the number is, the more important it is. You have your base priority, which basically says anything above this don't run, and anything below it you can run. And clearly this is showing you that everything should be runnable. Everything is enabled. You have your pending, you have your enabled, and you have your active. So everything here is enabled. Okay. We're running in our program, and then interrupt IRQ4 is fired off. Okay, and then we're just also indicating here, there's one where there's kind of software actions and hardware actions. All right, so the interrupt has occurred. If we go back to like here, or some of those early examples, the interrupt has occurred, so the pending bit gets set. Does that happen? Yes. Pending should get set, then stacking occurs. Hardware is going to go and stack your PC, your program status register, your link register, R3, R0 through 3, and R12. Okay. Then you're going to go in, your interrupt service routine is going to go off. So your NVIC figured out where the address is, switch your program counter to that. Now you're executing that stuff. So here you're off running this thing. Your pending has changed from 0, and now you're active, right? But the action of going into active has deasserted pending. And we've changed our base priority to 6, matching what this is, which means because our preemption priority said you can't have anything that's less important interrupting me, so how do you keep track of that? Well, you have a register here that says, here's your base priority. I can set that right here. So you can manually set it, or it's getting updated on the fly. All right, so that's there. Then what's going to happen? So then you're going to leave your interrupt. Okay, so your active status, oh wait. In that time, so you're going to unstack. You've unstacked your program stack. That's gone back to the, you're back into normal program execution, and active has been deasserted. Yep. Oops. And sorry, now you're back into your program execution in your base priority. Now that you've left that interrupt, your base priority has gone to 256. Yeah.
Was the base priority saved when we stacked? Or how did it know to go back to 256? Or is that like?
I don't know how it knows how to go back to that. You have a base priority register. So this is like the stat where you've set it. You've said this is what the base priority is. And so I assume it's just going to go back. That's where that state is held. And then this is going to, when it goes back to where it's actually keeping track of the base priority, and then puts that value in there. That's a good question. That's a naming convention problem, because the other one's called base priority, and this is like the status of the base priority, I guess. Yeah.
When you do the stacking, why is it that it says R0 to R3, but not the rest of them? R0 to R3 the least important?
So this is kind of like the call safe stuff. We're just going to say that we're going to assume that the interrupt is going to follow the ABI conventions, and it's going to use R0 through R3 as scratch space. And so when you write your interrupt routines, you'd have to use only that, and you'd have to save 4 through whatever. R12 is supposed to be for interprocedural calls. This would be a time when you'd want to do that. Usually the compiler does that, not necessarily you guys. Good question. Yep.
With a lower priority, like a higher number was called when number 6 was running, would it still set it to pending? Because you said the base priority would.
Ooh, we got some examples like that. Perfect question. Okay. So we can talk about nested interrupts. So what happens when a higher interrupt occurs? Oh man, bad higher priority interrupt, let's say. I got to change these things so we can keep our nomenclature clear. Occurs when the CPU is handling another of lower importance. So basically the incoming request has a lower priority number, so it's more important. Let's see, so a new interrupt occurs while you're in the current ISR. What's going to happen? Okay, so here, kind of back in this case, interrupt 4 has happened. We've stacked. We're in the middle of running the service routine, but a more important interrupt's going to happen. So we're going to interrupt 3, which has a priority of 3, so a priority number of 3. So that's lower than your base priority, so you should go and execute it, right? So what do you think is going to happen? Yep, so we're going to go stack. Now you're going to go stack the state of this interrupt, right? So from this point of view, the hardware has no idea how many levels deep you are in your inception of interrupts. Okay, you can, don't know. So here, we're just going to go and stack this up. We're going to go execute our priority 3 interrupt. So actually, let's see what happens. So priority 3 is in pending now. This guy's still active. They're all enabled. We're going to stack. IRQ number 3 is going to go off. It is active. It's no longer pending. We're going to execute this until we exit. Then we're going to unstack. We're going to unstack all the way back to IRQ 4. Then when we're done with that, we're going to unstack and be done. Yeah.
What happens if they're, like, during the execution of IRQ number 3?
Yeah.
If another IRQ level 3 interrupt occurs?
Then, but it can't, so it's of the same priority, then, so then it's going to go into pending, and then you would come back to it afterwards, right? So it's
After 3 or after 4 though?
after 3. Yep.
Why are we allowed to have the actives both active at once?
It's because they were both active.
Yeah, like they're just separate. The computer just like, this guy has lower valued priorities of higher importance, so I just address this active first.
Correct. And then it has to go back through. When you're unstacking, you have to figure out where's the thing you need to go to next. Right, so there's a process here, because you could have a lot of active things, and they might even be not in the same order you've done them. So there's no order in this bit. It's trying to go through and figure out what's the next one that has the sub-priority or higher priority, what's the next thing that should be done.
Would you use the stack in order to decide what's the next active bit that you have to handle?
The stack? I think they are going to use the active and the priority table to figure out what's the next thing that should go through. Okay. Yeah.
What if there's like 2 nested interrupts that like maybe change some variables and they're changing the same variables? Is that gonna be like a problem for the?
Oh yeah, that sounds horrible. Like you're like for some reason in an interrupt, you have 2 interrupts that can reconfigure a GPIO pin.
Yeah, something like that.
Yeah, don't do that. I mean, in simple cases, you can have a mental model of your processor in which it's unlikely those things are going to happen. But as your program gets much more complicated and you have more interrupts going off, then you can have these weird race conditions where something's going off and getting reconfigured. I mean, it'll still execute properly. It's not like it's going to have like, I don't know, bits don't get put in registers correctly when you're trying to reconfigure the GPIO. It just might not be what you intended.
Does an interrupt know if it's nothing on the stack yet?
Does it interrupt? No. Oh, so you're saying if interrupt 4 somehow got interrupt 3 and it was already stacked?
Yeah.
I don't think that can happen because of your priority table. I think your priority table is demanding that your stack is always increasing, as you go down, is always increasing importance or decreasing the priority, the priority number of the things. So it's never going to be like something's here and has to get put back on.
Yeah, the way I was thinking was like, if we run interrupt 4,
Yep.
and then we bring interrupt 2 and interrupt 3 on the same time. So 3 is going.
Yep.
3 is going to be the highest priority. So
Yep.
3 is going to start its stacking.
Yep.
We're going to run 3.
Yep.
3 is going to be finished.
Yep.
And then 2 is going to be there. It's going to be active.
Yep.
Or is it going to be just pending? Like
Yeah, it would be
doesn't-
pending.
Okay.
And then it has to go back and figure out, well, what is the most important interrupt I should service now
Right.
as it leaves unstacking.
So as it leaves 3, it'll say 2 is pending, but 2 is more important than 4. So
Right.
I'm going to stack up 2.
Because, yes, yeah. Yep. Okay. Any other questions? These are good questions. Yeah.
Kind of similar to this one you just asked, but like instead of 2, what if it was 1? It would just go to pending and execute interrupt 4 first.
Yeah. Yep. It's going to go by this, whatever you put in the priority table is the thing it will do next. Okay. All right, so we'll talk about tail chaining. This is one of the edge conditions I think you guys just brought up. When it's the same, you're interrupted by something the same or higher priority. So let's see how this one works. So we're in RQ4. A level 1 interrupt has gone off. So let's see, what would be level 1? Okay, so that's 10, right? So 10 has been put into pending. Or sorry, this is number 1. It has priority 10. 10 is smaller than 6. Or I'm getting my golf all backwards. 10 is larger than 6. And so this goes to pending, but it's not going to become active. So we're going to let, you don't want to preempt. You don't want to unstack either. So this is where you saw that little glitch before. It would just waste time to unstack. You already know you're going to go into the next interrupt. So if you have to go all the way back down to stacking and then stack back up, it would be a waste of time. So you say, well, I have another interrupt pending, no reason to unstack all the way. I'm just going to go do IRQ1. IRQ1 turns to active, and then we're going to execute that. Oops. And then when we're done with that, we'll unstack, because there's nothing else pending here. So it knows that you can unstack, and then you're going to unstack back to the program. Yeah?
So pending kind of decides whether or not we unstack or stack.
Yeah.
Interrupts.
Yep. All right. And our last edge condition here, late arrivals. So what happens if you're stacking, basically, and you get another interrupt comes in? So stacking is going to take a number of cycles. You could have another interrupt that occurs right then. All right, so what could happen? You don't want to do this. You don't want to say, so say you're in IRQ4, and then IRQ3 happens, right? You don't want to have to go and stack again. Doesn't quite make sense because it's the same information. So you don't want to stack this twice. So you just say, okay, basically what's going to happen is in the last cycle of stacking, it's going to go recheck what's pending, what's the highest priority of pending, and then push that to active. So even though IRQ4 is the thing that started the stacking process, because IRQ3 came in late, it's going to be more important or a lower priority, and we're going to execute that. So then you're going to go execute IRQ3. Now, if we look, IRQ4 is still pending. It never even started executing, never went to active. It's still pending. So as we get out of IRQ3, we're going to do tail chaining, which is we're just going to chain them on one after another. No reason to unstack. Then we're going to do IRQ4, unstack all the way down to the end of the program, because at that point, nothing was pending. Yeah.
For the other cases, is it always checking to see if like during the stacking process, or when the stacking process is done, is it always checking to see which priorities that are active has the lower priority?
Yes. Wait. Is it always checking to see which one is which active? You don't become active until you've stacked. So I don't think 4 is not active here, and 3 is not active.
Sorry, I meant the pending.
Okay, yeah. So now you're going to basically go just at this last time frame here. It goes through and says, okay, which one's pending, which one has the lowest priority, most importance, and then it executes that. So basically, the combinational logic of trying to figure all that out, essentially in one clock cycle, starts getting larger and larger and larger. And now that's why NVICs usually don't want to have 240 interrupts if you don't need them. Keep it smaller. Okay, what questions? You have any more questions? Yep.
Where does the preemptive and sub-priority numbers play into this? Like, would there be like another base priority kind of thing?
Yeah, so you could imagine we could, this is a toy example, but there would be 4 bits here allocated in some way, either all sub-priority or all priority or something in between. And so if you had a priority, something of equal priority, and they were puts them in pending, and then this decides the order of servicing things that are pending. So say we had, back to this example. So what was this? This was IRQ 1 was of least importance, lower importance compared to IRQ 4. If IRQ 1 happened to be the same priority but a lower sub-priority, then it would go next. Okay. But it would not be allowed to interrupt because it has the same preemption priority. So you don't preempt yourself for your things of the same priority. Okay. What other questions do you have?
I have a weird, conceptual question.
Okay.
It's really annoying going back to this priority table over so that like the most important person is just at the top of the priority table?
I mean, essentially, that's what the NVIC is doing. You just don't have to write that. You don't want to have the core responsible for that. So the compiler, in some ways, is doing that. You could say, yeah.
And all of these bits and everything are stored in registers.
Correct. So as part of your program status register, you have your active. I think you have your base priority. But yeah, all enabled and pending. These are all registers that we kind of defined up above in the slides.
We're not allowed to write to them, or just reading?
I guess we have to check to see which ones are read-write. But the priorities table you can. I think you can write to pending and enabled. I don't know if you can write to active or not. I think you can only write to pending, and then you could force an interrupt to occur by writing to pending, and then when it got to the priority level that it was able to be serviced, then it would be serviced. All right. So we can recap here. There's a bunch of new registers to understand how they work. We highlighted a bunch of those in green, so you can enable register, or you can enable and disable interrupts. You have separate registers for that. You want to clear and pending, you have separate registers for that. A minor detail just to keep track of when you're frustrated in lab and you're like, I'm putting bits in here, nothing's happening. You can remember that there's two addresses. You have to set your interrupt priorities, and there's two concepts here. There's your preemption priority, which means things of this value can only be interrupted by things of smaller value, using the Gulf rules. And then there's a sub-priority. It means even if I'm at priority 4 and I have another interrupt at priority 4, I'm not going to be serviced. I'm not going to do anything about that until until I get out of this interrupt, and then it's just telling you what's the order of them. So if you had 10 interrupts go off all at once of all priority 4, sub-priority is going to tell you what the order those interrupts should be done in. So there's maskings that allows you to temporarily disable interrupts, or at least groups of interrupts, which is a nice feature to have. And then there's all the edge conditions that you could imagine, basically preemption, tail chaining, and late arrivals of what happens from a timing point of view as different interrupts occur. All right, we'll end there, and we'll go over one more interrupts example on our next lecture, and then we'll move on from there. So if you could turn in your worksheets when you're done, on your way out, that would be great. All right, thank you.
What day is it? Thursday? Hey, y'all.
Oh, yeah. After that lecture, you need lots of service.
Yeah. So according to the Gulf rules, I just want to ask a question. So for the preemption priorities and so like let's say for a specific I don't know. Just say it's not Thursday. Does that
I don't mind.
I want to listen to what he's saying.
Oh, okay, that's good.
How's it going?
Oh,
Thanks. All right.
Yeah.
We have a bit of I can take a look. Oh wait, wasn't there some code we had to write outside the lab too?
What if this one What is
I thought there was some part that we had to.
value of R0 to R3 that was originally has a certain value of variables. Isn't
Well, the program has never, the program doesn't call an interrupt.
Oh.
So you're not passing values to an interrupt. It's not possible. Or at least not what you should do.
So the R0, it's not like a function like so R0, R3 is going to be like a kind of input variables. It's not.
How
like,
does interrupts get called?
Just by the peripheral, something like that. Like
Yeah. So, but we don't use code. Does not call a peripheral to go and raise something high, right?
Oh,
This is-
okay.
You've configured a peripheral. Maybe like a pin goes high on a GPIO pin, and that will cause a wire, a line, to go from 0 to 1. It will trigger the NVIC to do something.
Oh.
So there's no like the main program is not causing this to happen.
Oh, it's nothing. So you don't need any variables about that. You just have to stack the PC and those kind of important registers.
You don't have to pack the hardware stacks the PC.
Oh, okay.
And all that sort of stuff. So you don't have to do it from person writing main. These things just happen, and it's kind of like waking up from amnesia. You're like, oh, you know, why all these clock cycles went by? I don't understand, right?
Okay.
But it should be very transparent.
Oh, okay. So this gray area is like this one is like unnecessarily stacking. It's just like
It's just telling you this is what you would be doing in stack, but you don't have to unstack and restack. So I think it's going to take 2 cycles or something.
oh, so
figure
it's,
that all out.
so this one is meaningless. This gray area.
I mean, it's tail changing. It's just indicating that we're paying attention to this idea of stacking.
Oh.
It's just,